Hello APC Mechanics students. In Unit 4 System of Particles and Linear Momentum, Class 5 4.3 Conservation of Linear Momentum Collisions, Part 1. Then let's start Section 1, Collision and Conservation of Linear Momentum. Consider two objects of masses m1 and m2 and of respective speeds v1 and v2 heading toward each other and about to collide. Then basically the first object is traveling toward the right with the speed v1 and the second object is traveling up with the speed v2. Each object has a linear momentum of p1 is m1 v1 and p2 is m2 v2. Before collision, the total linear momentum of the system is the sum of p1 and p2. Now they're gonna collide. The two objects will collide after collision, and if we suppose that the masses do not change, there will be a redistribution of speeds and the objects will acquire new speeds given by v1 prime and v2 prime. So after they collide, we expect that the speeds of each particle will change. The first particle will acquire a new speed given by v1 prime and the second particle will acquire a new speed given by v2 prime. Alright? Now, hence their new linear momentum is given by p1 prime and p2 prime respectively. After collision, the total linear momentum of the system is given by p prime, which is p1 prime plus p2 prime. Suppose our system includes both objects 1 and 2. So before here I move on to the following, let me recap the following. So basically before collision, the first object has a linear momentum given by p1 and linear momentum given by p2 for the second object. The total linear momentum of the system will be given by p. After collision, the linear momentum of the first object will be given by p1 prime and the second object will be given by p2 prime. Therefore, the total linear momentum of the system after collision is p prime. If the system is isolated and includes both objects 1 and 2, and let's assume that our system is isolated from external interactions, that is, no net external forces are acting on the system, then F net is 0. Why F net is 0? Because we're considering it to be isolated from external interactions. Alright? But according to Newton's second law, F net is dp by dt, which means, but which p here? So here we can talk about several p's. We can talk, for example, about the momentum of the first object, the momentum of the second object, or the momentum of the system. Since here we're considering the system to include both objects 1 and 2, then we're talking about the momentum of 1 and 2. So that would be the total linear momentum, which is equal to p1 plus p2. But which p? p1, p2 are the total linear momentum of the system p. For sure, we're talking about p of the system simply because our system is containing the objects 1 and 2. And then we have the dp by dt is 0. Why? Because we're saying that F net is 0. We're saying that F net is 0, but we know that F net is given by dp by dt, which means dp by dt equals to 0. Which means dp is 0. So here if we have a fraction and the fraction is 0, so the numerator is 0. And dp means p final minus p initial, which means p initial is equal to p final immediately before and after the impact. This means that during collision, and if the system is isolated, no external forces are acting on the system, the linear momentum of the system is conserved, and this is a very important property of the system. So always during collision, and if the system is isolated, our linear momentum of the system is conserved. And we have that p initial is equal to p final, which means p1 plus p2 is equal to p1 prime plus p2 prime. The total linear momentum of the system is conserved, but the linear momentum of each object is not the same before and after collision. And here let me do the following remark. So p1 is not equal to p1 prime. p2 is not equal to p2 prime. However, p1 plus p2 would be equal to p1 prime plus p2 prime. And this is coming from the fact that our system is isolated, because F net equals to 0 and F net is given by dp by dt is equal to 0 whenever the derivative of something is 0, which means that this itself is constant with respect to time. Or you can consider it as dp is equal to 0, which means p initial minus p final equals to 0, which means p initial is equal to p final. Alright? For object 1, now let me also clarify something. The change in momentum is given by delta P1, which is P1 prime minus P1, and this is given by the impulse J1, which is the impulse exerted by the object 2 on the impulse 1, on the object 1. So delta P1 would be the change of momentum for the object 1, which is P1 prime, which is the final momentum, minus P1. That would be J1, which is the impulse exerted by the object 2 on the object 1. Similarly, we can talk about delta P2, which is the change in momentum for the object 2, which is J2, which is the impulse exerted by 1 on 2, which is the impulse exerted by 1 on 2. Now, considering again the equation which states the conservation of momentum, the conservation of momentum means it is equal, which means P1 plus P2 is equal to P1 prime plus P2 prime. Then let me do the following. Let me drag P2 to the right and P1 prime to the left. That would be P1 minus P1 prime equals to P2 prime minus P2. But we know that delta P1 is P1 prime minus P1, which is J1, and delta P2 is P2 prime minus P2, which means minus J1 is equal to J2. Then the impulse exerted by 2 on 1 in magnitude is equal to the impulse exerted by 1 on 2. And this is nothing but Newton's third law for interaction. Now, what about specific types of collisions? Collisions are classified based on the kinetic energy of the system. The kinetic energy of the system before collision is given by K initial, which is the kinetic energy of the first particle, and the kinetic energy of the second particle, given by half m1 v1 square plus half m2 v2 square. And the kinetic energy of the system after collision is given by Kf, which is K1 prime plus K2 prime, half m1 v1 prime square plus half m2 v2 prime square. If the kinetic energy of the system is conserved, which means kinetic energy initial is equal to kinetic energy final, then the collision is said to be elastic collision. The collision is elastic whenever the kinetic energy of the system is conserved. So we can talk about the kinetic energy of the system before collision and after collision. If these two quantities are equal, then the collision is said to be what? Elastic collision. If the kinetic energy of the system is not conserved, which means for some reason kinetic energy initial is not equal to kinetic energy final, then the collision is said to be an elastic collision. Then basically collisions are classified into elastic and inelastic, and this is based on the fact that whether kinetic energy initial is equal to kinetic energy final or not. If they are equal, then it is elastic. If they're not equal, it's not elastic. What is the kinetic energy of the system? It's the sum of the first and the second before and after collision. Exercise 1. Particle A and particle B, each of mass capital M, move along the x-axis exerting a force on each other. The potential energy of the system of two particles associated with the forces given by the equation. U is beta over r square, where r is the distance between the two particles and beta is a positive constant. So this is our system that consists of A and B, and because we're talking about the force exerted between B and A associated with this potential, which means this is an internal force and there are no external forces acting on the system, which means that our system is isolated, and by that the linear momentum of the system is conserved. At time t is equal to 0, particle A is located at x is equal to 2d with an initial speed of v0 to the left, and particle B is at rest at the origin as shown on the figure above. At time t is equal to t1, particle A is observed to be traveling with the speed 2v0 over 3 to the left, the speed and the direction of the motion of particle B. So what's happening here is that before collision the speed of the particle B is 0 and particle A is moving to the left to the speed v0. Not before collision, at the instant t is equal to 0. After a certain time interval, whether there is a collision or no collision, it happens that particle B will be moving with a certain velocity v and particle A would be moving to the left with the speed 2v0 over 3. Now, because our system is isolated, we can say that P initial is equal to P final, and that would be the conservation of linear momentum. And if this is a free response question, we should mention that since our system is isolated, then apply the conservation of linear momentum. Initially, particle A is moving with a mass m and the velocity minus v0 to the left. B was at rest. After a certain time interval, t is equal to t1, A is moving to the left with the speed minus 2v0 divided by 3, and particle B is moving with the velocity v to be determined. Now mass cancels with mass cancels with mass, then minus v0 is equal to minus 2v0 divided by 3 plus v, then v in this case would be given by minus v0 plus 2v0 divided by 3, which is minus v0 divided by 3, which means that's moving to the left with the speed of v0 divided by 3. Okay. Now, exercise 2 data were collected during an experiment that used two identical cars, car 1 and car 2, moving along a one-dimensional track. Car 1 moved toward and collided with the stationary car 2, and data were collected. So car 1 is moving, this is the initial speed of car 1, and that's the final speed of car 1. Now car 2 initially the speed was 0, so this is 0, 0, 0, and the final velocity is given by these. The data collected just before and after the collision are shown below. What conclusion can be made about the data taken in this experiment? Now, if you think about it, we know that during collision, the impulse in magnitude, or let me say one is negative to the other, so in magnitude they are equal. So here we're talking about the magnitude, which means m1 delta v1 is equal to m2 delta v2, which means that m delta v is constant. So whenever delta v becomes greater, this means that the mass should decrease. So whenever two numbers multiplied by each other are constant, whenever one of them increases, the other would decrease. Now here, if you notice carefully, we can calculate delta v for each car. So delta v here in this case, what do we have here? It's 7.7 because the initial speed is 0. So delta v for car 2 would be 7.7, 15.9, 24.1, and for the first car would be given by 10 minus 1.5, which is 8.5, and that would be 17.5, and that would be 26.5 if we do the difference. So notice that delta v 1 is greater than delta v2, which means mass 1 is less than mass 2. Okay, based on this relation, which means that car 2 was more massive than car 1. Now exercise 3, the uniform rod of length L shown above is supported by holding an end X so that the rod makes an angle 60 degrees with the horizontal floor. There is no friction acting between the rod and the floor. When the support X at X is removed, the rod falls under the influence of gravity. Which of the following best describes the movement of end Y as the rod falls? Although this problem seems to be complicated, but it's straightforward by referring to the center of gravity. They're asking us if the rod, so we're holding the rod from here, from X. What we're gonna do is we'll release the rod. We need to see how much Y will move to the right relative to the right, or to the left relative to the initial position. Now, because the rod is uniform, which means that the center of gravity would be at the middle, then the motion of the rod is modeled by the motion of the center of gravity under the influence of gravity itself, the center of mass. So basically, under the influence of gravity, the center of mass will fall here to this position, which makes Y moves to the right. Now the thing is that we need to find this distance. So the center of gravity would fall to this point. Now we need to find this distance. If this is A and this is Y and this is B, then cosine 60 is given by AY divided by L over 2. Because this is a uniform, then this is L over 2, which is the distance from Y to B. Then AY would be given by L over 2 times cosine 60, which is L over 2 times half, and that would be L over 4. Then basically this distance here is given by L over 4. Now if it happens, if the center of gravity falls down, this means that Y will move, and this distance would be L over 2, which means that Y will move to the right by a distance of L over 4. Now exercise 4, a ball is initially moving horizontally with velocity vi as shown above. It is then struck by stick. After leaving the stick, the ball moves vertically with the velocity vf, which is smaller than in magnitude than vi. So vf is smaller than vi. Which of the following vectors best represents the direction of the average force that the stick exerts on the ball? We know that the average force is given by delta P over delta T, but delta P is m delta V divided by delta T. Then basically the direction of the average force is the same as the direction of delta V because m and delta T are positive. Then delta V, and they are scalars. So F average has the same direction as delta V. Now delta V is given by V final minus V initial, and this can be utilized as Vf plus minus Vi. Now this is Vf, the first thing, so Vf is up. Now Vi is to the right, then minus Vi would be to the left. And if we add these two vectors, it would be something like this. So it's either B or D, but it's more likely to be B because Vi is greater than Vf. Now a 2 kg ball collides with the floor at an angle theta and rebounds at the same angle and the speed as shown above. So this velocity vector is the same as that. Speed and direction is the same. Which of the following vectors best vector represents the impulse exerted on the ball by the floor? J is basically delta P, which is m, or let me say, m delta V. Then J has the same direction of delta V because m is a scalar, which is positive. Delta V is V final minus V initial. This is V final, and that would be V initial. This can be understood as m into Vf plus minus Vi. Then we need to add Vf and minus Vi. Vf would be upright, minus Vi would be up left. If we add them, the horizontal part to the left will cancel the horizontal part to the right, and we will have a vector which is pointing up like that. And that would be delta V, which has the same direction of J, and E would be the correct answer. And exercise 6, which is an exit ticket for today's video, an object having an initial momentum that may be represented by the vector above strikes an object that is initially at rest. So before collision, because they will collide, we have two objects. This is the momentum of the first object, and the momentum of the second object is given by 0. Then initially Pi plus Pf is given by the following vector. Which of the following sets of vector may represent the moment of the two objects after collision? We know that if the system is isolated as we suppose, then P initial would be equal to P final. So this should be P1 plus P2. That would be P1, and P2 would be 0. So P initial would be P1 plus P2. Now, because we suppose that the system is isolated as we said, then the final momentum should be equal to this plus that, which is basically equal to this one. Now, if you notice, if you look at A, these two vectors have the cancellations effect. So if you add them, they won't give you this vector. So that's wrong. Now, for B, if you add these two vectors, it would give you a vector which is greater than this. So that's wrong. Now here we would have the cancellation effect. We would have a vector which is pointing to the left. P1 plus P2 is this vector which is pointing to the right. So if we add them, we would have this vector which is pointing to the right. Now in D, so we might have the up component to cancel with the down component. So up cancels with down, let's say, but it's not completely true. And partly left will cancel with right. So we would end up a vector which is very small pointing toward the right, which is not equal to this one. However, E would be considered to be correct. First, let me repeat just why part D is wrong. For part D, if you notice carefully, this vector can be decomposed into two vectors, one which is pointing right and one which is pointing up. And this vector can be decomposed into two vectors, one which is pointing down and one which is pointing left. So let's suppose that this cancels with that. it's not completely true, because we know that this is greater than this one. However, now with the left and right, we would have the cancellation effect, and we would end up with a vector which is pointing to the right, but it's very small, which is smaller than this one. For this reason, D is wrong. Now for part E, if you notice carefully, this can be decomposed into up and right, and this vector also as well can be decomposed into down and right. Now this vector up cancels with down, and we're left with two vectors adding up to the right, which would give us this vector, which makes E to be the correct answer. Then that's it for me in this video, guys. See you soon in a new one.